All right, in this section, we are going to be looking at polynomial functions and their graphs. We've already seen some basic versions of this, but we're going to dive in a little bit deeper on this. So just as a reminder, a polynomial is something, well, it kind of has this generic look for the function we're seeing here, right? But some examples, some things we might be used to are things like, f of x equals 5x to the 6th minus 2x cubed plus x squared minus 11. Something like this, where we have whole numbers for the powers here. We only have the one variable x. We don't need every single power, so notice we don't have anything to the 5th or the 4th. We don't have an x term. That's okay, but just something along these lines where we have whole numbers for the powers and then real numbers for these coefficients. And the coefficients, again, are these numbers in front of the variable portion. Okay, so the graphs of these, again, we've looked at some of these pretty closely, at least linear and quadratic, but we'll extend this to cubic and quartic and quintic, which is to the 5th power, and so on. And we'll start to see some patterns. So linear, we kind of know what that looks like. We're increasing as we go from left to right. Same thing for a cubic, x to the 3rd, and the quintic, x to the 5th. So we're kind of increasing as we go left to right. We notice that near 0 here, we flatten out a little bit more. For the even powers, for x squared and x to the 4th, we decrease and then turn around and increase. Notice that x to the 4th near 0 is a little bit flatter than x squared is. And we can imagine x to the 6th would be even flatter than that near 0. Okay, so let's start with some functions that we can just kind of use basic transformations on to see what their graph looks like. So we know what x cubed looks like. All right, so this is, we'll just treat x cubed as like the original function. So I'm going to draw all of these on here real quick. So x cubed, we can go back and say, okay, cool, that was one of the basic ones here. But basically that will pass through the point 0, 0, but also the point 1, 1, and negative 1, negative 1. All right, and then we'll have a shape something like this, right, increasing as we go left to right. But then we have this additional piece with the negative, right? This is going to be a vertical reflection. So that's going to say, all right, let's flip this vertically or over the x-axis. So that means that we're going to have something along these lines in green here. And then the +1, that's just going to say, let's move up 1. So take the points that we have, move those up 1, but otherwise the shape will pretty much be the same. So the red is going to be our final graph. It's probably a little bit smoother there, a little bit more rounded by 1 there. So then we can give the domain and range. Well, the domain for polynomials is just going to be all real numbers. And sorry, usually I do a colon here. So here is the domain. And then our range, in this case, because it's an odd function, right, x cubed, we see that we can get all the positive numbers we want, all the negative numbers we want. So this range is also all real numbers. For q of x here, again, we can say, well, let's start with the most basic function, right? So x squared is going to be the basic function. So x squared is going to pass through 0, 0, 1, 1, negative 1, 1. And if you want to go further, you could say negative 2, 4, and 2, 4, right? But we're just kind of looking for a sketch. When we say sketch, we're looking for general shape here. So it doesn't have to be perfect. We just want to get a general idea of what's happening. So, okay, looks something like that. The +2, remember inside the parentheses works a little bit backwards. So this actually means let's move left 2. So we can take all of our points and shift them over left 2, right? So we're just kind of moving all of these points over. And if we connect those dots right? We get the same shape as what we had in blue, but just shifted over a little bit. So these are kind of things we've done before to get a sense of what's going to happen to our function. Okay, another thing we're interested in is end behavior. So what happens to the function in the long run? So that's either as x becomes very large in the positive direction or in the negative direction. So basically, as we're looking to the right, that's x goes in the direction of infinity, or it tends to infinity, and then looking to the left as x goes to negative infinity. So we're curious, okay, what the end behavior, we're talking about the y values. What happens to y as we do this to x? And the nice thing is we can break this down in terms of even and odd degree. So if the highest power, that's our degree, if the highest power is odd, then we have some very distinct conclusions that we can make. So we can say, well, great, if it's an odd degree and the leading coefficient is positive, right? We have two different possibilities. Leading coefficient is positive versus negative. Well, if it's positive, it's going to look some version of like what that generic linear and cubic and quintic function look like, right? It's going to increase as we go left to right. But if it's a negative leading coefficient, it'll flip, right, reflect over the x-axis, so it'll decrease as we go left to right. So the end behavior is kind of saying, okay, if I were to put an arrow at the end of our function here, where is it going, right? The y values, are they going up to infinity or are they going down to negative infinity? Even degrees, these ones are, in my opinion, a little bit nicer because they're always in agreement. So either both ends are going up or both ends are going down. If the leading coefficient is positive, right, then everything is going up. You can think about a basic parabola, right, y equals x squared, as sort of a point of reference. And if that leading coefficient is negative, then both sides are going to be pointing down. So that's pretty consistent, right? Positive coefficient, everything's going up. Negative coefficient, everything's going down. So the evens, again, are a little bit more straightforward in my opinion. Okay, so let's figure out the end behavior for a couple polynomials. So the first thing we want to do is say, okay, what's our, well, do we have an even or odd function? Right, so we look here and we say, well, what's our highest power? Let's look at that term. And that highest power that we have is 3, right? So it looks like that power 3, that's going to be odd, right? And then the other question we want to ask is the coefficient positive or negative? And that's, again, the coefficient's the number in front of x cubed. So that's negative square root of 7. So I guess that's negative. So we have the combination of an odd function with a negative coefficient. So we can refer back to this. What I would say is, don't really memorize these. Use basic functions as a guide. Like I had mentioned over here, y equals x squared is a very simple even function. It sort of represents what happens for all even functions. You could do the same thing with y equals x cubed, right? Get a sense of what happens there. That kind of tells you in general what all odd degree polynomials are going to do with a positive coefficient. So in this case, we have a negative coefficient though, so it's going to flip, right, a vertical reflection. So as we look to the left, our y values get larger and larger. As we look to the right, they get smaller and smaller. So what we're going to say is, okay, as x goes to infinity, so as we go to the right, our y values are actually getting smaller and smaller. But as we go to the left, right, so this is to the right, and then as we go to the left, as we look to the left, our y values are getting larger. So in general, this thing has a shape, right, something like this. We don't need to know exactly, right? So we don't even need to put this into a calculator or try to, do any factoring or anything like that. All we need to know is even or odd, and then do we have a positive or negative coefficient, and we can make some strong conclusions. Okay, similarly for this one, let's do the same thing. So even or odd. And we find in here, right, the degrees are not always, or the degrees of each term are not always in order. So here's our linear term, then our cubic, then our squared term or quadratic term. Okay, but our term with the highest power is this negative 2.84 x to the fourth. So that's going to be an even function. And then is the coefficient positive or negative? Well, it looks like it's negative. So that means we have something that opens down, right? And more likely this thing probably has some kind of, other movement within it. But the important thing is this is opening down, right? Both sides are in agreement. So the y values, whether we look to the left here or to the right here, right, as x goes to negative infinity or to positive infinity, we get those two sides to agree. The y values are going down to negative infinity, right, or in the direction of, I should clarify. So when I say to negative infinity, that's not a place, it's a direction. Okay, the intermediate value theorem basically says that you can't jump over anything. If we have a continuous function, which all of these polynomials are, if I have two different y values, then I'm going to hit everything in between those two values. So in particular, where we use this is identifying zeros of a polynomial. So in this picture, we can see that c is one of the zeros of the polynomial. It makes the y value 0. So if I know, for example, that plugging in a gives me a negative y value, and plugging in b gives me a positive y value, then somewhere in between a and b, there's got to be a 0, right? So that's usually how we use this, though it can be used for other things. And this note at the bottom is, if p of a and p of b, so the y values at a and b, if these are not the opposite sign, so if one's, if they're both positive or both negative, there's not a whole lot for us to conclude about zeros. Okay, so let's use that intermediate value theorem. Let's try to figure out, okay, what is p of 2 and p of 3? And what we're hoping is that one of these is positive and one of them is negative, just like in our drawing here, so that we can conclude there's a 0 in between them. So we can just plug in 2 and 3, right? We could say this is negative 2 cubed minus 2 squared, 5 times 2 plus 10. And we could say this negative 3 cubed minus 3 squared, 5 times 3 plus 10. Remember that when we have a function, f of x or p of x, replace the x every place that it shows up. So in this case, we're putting 2 and 3, we're putting those in 3 different spots. Okay. So let's actually figure out what those are. So p of 2 and p of 3. All right, if we work through everything, I think we'll find that p of 2 is positive 8. And then p of 3 is negative 11, I believe. You can double check those with your calculator if you'd like. I'm just kind of doing those in my head real quick. But the good news, right, is that one of these is positive, one of them is negative. So p of 2 is 8. Let's just show where that is. That would be a point over here. And then p of 3 is negative 11. So that would be down here. Right, so we don't exactly know, or we don't even need to know, what the shape of the function looks like between 2 and 3. What we know is that this is a polynomial, so it's going to be continuous. So no matter what it does on its way from one point to the other, it's got to pass through everything. So maybe it looks like this, all right? Maybe it looks like this, we don't know. So our 0 could be here or maybe here. All we know is that there is going to be a 0 there somewhere. So we're going to use our calculator to figure out what that 0 actually is. So, all right, how would we do that? Let's go to y equals and put in our polynomial. Make sure you're using the negative button here, not the minus button. Negative x. We can use this little caret to raise it to a power. Minus, this time we do want the minus, x squared plus 5x plus 10. Okay, so if this is the case, let's take a look at our graph. We might have to adjust the window, of course. No, it looks okay. Well, let me just back up a little bit, change our y value. So let's say we're going from negative 20 to positive 20. Okay, so this just gives us a little bit better view of what's happening. So, right, the curvature between 2 and 3 looks kind of like one of the two that I drew on our graph. Anyway, if we want to calculate that 0, let's do second and then trace. And our second option here is 0. And let's choose a left bound, something left of that 0. And then we'll scroll over a right bound. And the arrows will indicate your 0 is somewhere in here. Hit enter again, and then we've got a 0. We're going to approximate this to the nearest hundredth. So 2.53, 2 decimal places. So x equals 2.53, or another way to say that is p of 2.53 is 0, right? That's what it means to be the 0 of a function. Okay, the next thing we look at is multiplicity. So sometimes we have a 0 that can have, right, multiplicity of just 1. That's kind of a common case. But we can have something certainly with higher multiplicity. We'll look at a couple examples, but this is basically saying if you have a linear factor, if it's taken to some power, that's the multiplicity. Okay, so if one of our linear factors, meaning a 0, has a multiplicity of 1, we're just going to cross the x-axis, no problem. And that's kind of like the one that we just looked at over here. We just cross through the x-axis, no problem. But if we have even multiplicity, then we're going to bounce off the axis. So we're not going to cross it. We're just going to sort of touch the axis real quick, turn right back around. And if there's odd multiplicity, greater than 1, so 1 we just pass through, but greater than 1, we still pass through, but we kind of level off just a little bit. So it's a little bit flatter at that point. So that's kind of the difference between y equals x, right, which is our function, oops, right, where we just kind of have a line through there, y equals x. We just zoom through the axis. But this is something more like y equals x cubed, where we level off a little bit as we're passing through. All right. So let's see an example here. So I'm giving us an equation and sort of calling out all of the different things, thinking about, okay, why do these line up? So let's look at x plus 5 squared. So this means that we have a 0 of negative 5, right? What makes x plus 5 0? Negative 5 in for x. So at negative 5 over here, this is why we bounce off the axis, right? We have an even power, even multiplicity of 2. So anytime that happens, we bounce off the axis. Okay, our next term, x plus 1, that means we have a 0 at negative 1. That's what would make this 0. It's implied that the multiplicity is 1, right? If we don't have a number up there, it's just going to be 1. And this one, we go straight through the axis, right? We don't even flatten out. We just kind of go straight through. X minus 4, okay, so this means we have a 0 at 4. That's got multiplicity 3. So we should also go through the axis, but we're going to kind of round things out just a little bit as we go through. So we're not just going to race through like we did at negative 1, but we're going to sort of smooth out a little bit, kind of take almost like we're going to slow down, take a little break almost. And then x minus 7, we've got a 0 at 7. In this case, again, we have just multiplicity 1. So we're going to zoom right through the axis there. Now, the only other piece is that, hey, there's a negative out front here. What does that do? We might not know as we're going through whether the x plus 5 squared, so okay, or 0 at negative 5, does it bounce up this way or does it bounce the other way, right? Which way am I passing through the axis at negative 1? This is just a product of saying, hey, okay, let me look at all of my powers. 2 1, 3, and 1. If I add all those together, I have an odd function, right? Something of odd degree. Normally, an odd degree function would increase as we go left to right. If we want it to decrease, we got to toss a negative in front, right? It's got to have a negative coefficient, so that's why it's got to be there. Okay, so let's talk about using those zeros to graph polynomials. We've done this before with just quadratic functions, right? Graphing parabolas, but now it's a little bit more involved. So we'll refer to this process as we go through a couple of examples. But the very first thing we would do is set the polynomial equal to 0, factor it, and then set each factor equal to 0. That's kind of the major thing. So if we have a function like this, x squared plus 8x plus 16, we can say, hey, I know that that factors to x plus 4 squared. And if you're not totally sure about that, right, think about we need two numbers that have a product of 16 and a sum of 8. And you'd pretty quickly come up with the fact that the two numbers you need are 4 and 4. So we'd have, right, two factors, x plus 4, x plus 4. Another way to say that, x plus 4 squared. All right, so we have a 0 at -4, right, or the point -4, 0. It's another way to say that. And then we have multiplicity of 2, right, which means that we're going to bounce off the axis. That's how I like to say it, is I just bounce off the axis. So let's go to -4 over here. And we say, okay, well, that's great. I'm going to bounce off the axis, but am I doing that from above or from below? And the other way that we know this, right, is we have an even function with a positive coefficient. So that means it's going to look pretty much like x squared, but maybe just shift it around somewhere. So that means we're going to be opening up. So if that's the case, right, we have something maybe like this, again with a little bit of curvature here. Make sure it doesn't look like a V. It should have more of a U shape to it. But basically, that's the idea behind it. All right, so that one's pretty straightforward. So our degree is 2. Our multiplicity for the 0, -4, is also 2. And that's why we bounce off the graph at -4. Okay, let's look at one that's a little bit more involved here. So for starters, let's find our zeros, right? And I'll just list the x values for those. So look at each factor and set them equal to 0. So we're going to say, okay, x is the first factor, set it equal to 0. X minus 2 is another factor, set it equal to 0. X plus 1, set that equal to 0, right? Figure out what the x values are that solve each of these. Well, x equals 0, that's done for us. X minus 2 is 0, I guess that means x is 2. And then x plus 1 is 0, I guess that means x would be -1, right? We can just move the 1 and the 2 to the other side. So here are our zeros, but they also have different multiplicities. So, right, the multiplicity for our 0 of 2 is 3. The multiplicity for our 0 of -1 is 2. And the multiplicity here for x, right, or for our 0 of 0 is just 1. So if we want to determine the degree, so the degree of this polynomial is 6, right? It's the sum of all these multiplicities. Basically, what's our largest power of x if I were to multiply all this stuff out? But please don't actually multiply all that stuff out, right? It would take a lot of time and wouldn't be worth it. The zeros of the polynomial, okay, well, we found all of those zeros, so we're good to go. So those are the two things it asks, but then it says draw a sketch of the graph again. So, okay, start with your zeros. So let's say we've got zeros at 0 and +2 and -1. We know that we have even degree, right? Degree 6 is even. And we have a positive coefficient, right? This if we multiply everything out, there's no negative to make that leading coefficient negative. So positive coefficient. So even and positive coefficient means it should open up like this. But probably more realistic, again, it'll have like some bumps along the way. And that's probably where these zeros are going to come in to help us out. So, okay, let's figure out what happens at each of these spots. So first of all, the end behavior, we can say, okay, what happens to the left of -1? It looks like we're going to be increasing, right? So we're going to have something like this. And to the right of 2, we're also going to be increasing. So the end behavior is a place we can start. We know that because what we talked about previously is an even function positive coefficient. Okay, so let's fill in the gaps. What happens at -1? Well, this has multiplicity 2. So we should be bouncing off of the axis. So instead of going through the axis, we're going to have a little bit of curvature here. We're going to bounce off. But what we know is I can't just keep going, because otherwise I'll never hit this other 0. So I probably bounce off, but then turn back around. So what happens when we hit 0? Well, that has multiplicity 1. So I'm going to go through the axis. Okay, but then we also know this has got to turn back around, which should be verified. Hopefully I've got some sort of odd degree at 2 that allows me to go through the axis. And sure enough, at 2, I have an odd degree of 3. The only thing we might want to be careful about is smoothing that function out. Remember that if we have an odd degree that's bigger than 1, then when we come back through, we're going to sort of level out a little bit before we carry on. So round it out just a little bit and then carry on. So this isn't the greatest graph in the world, but we can go over to our calculator. Let's just verify that we had, at least to some degree, the right idea of what was happening. So x minus 2 cubed. Can use the little caret for cubed, and then x plus 1 squared. Okay, let's take a look at the graph, and maybe I'll adjust my window to kind of match what we have. So let's say we're going from -5 to +5 in both directions. Hey, not too bad, right? It looks like we go a little bit farther down in between 0 and 2 than maybe what I did, and maybe even a little bit farther up between -1 and 0. But this is also why it's a sketch. So the idea of a sketch is to get the rough shape of a thing, not to be perfect. So you don't need to fill out a table, get everything perfect. We're just kind of using those zeros and then working from there. Of course, mine's not very nicely curved in here, but I'm doing it by hand, but same general shape. And that's sort of the important part of what we're doing. Okay, once we have that, we can talk about local max and min values, right? Maxima is the plural of maximum, and minima is the plural of minimum. So these are just the highest and lowest points. Now we can say local max and local min because it might not be the largest or smallest point for the entire function, right? Especially with these polynomials where we know they keep growing or keep falling. There may not ever be a global max or min. So sometimes all we have are these local values. For various degrees, right, we can kind of do the same thing that we've done before, talk about even and odd. So for even functions, right, as something like a quadratic, we're going to have one turning point where we have this vertex here, and the vertex is either going to be our min or our max, depending on what situation we are in, right? So here's our min, here's our max, right? Just depending on if we open up or down. For degree 3, meaning a cubic, the basic graph doesn't have local max or min. It kind of slows down in the middle here, but it doesn't actually drop back down before going up. But if we have some variation on this, like x cubed minus 2x squared plus 3x, something more involved, it's going to get some extra curvature. So it's going to end up getting a max and a min. Or if we have a negative coefficient, right, same thing, we'll get a max and a min, but just in the other order. Right. So as far as turning points go, you can turn around one fewer time than whatever your degree is, right? So for a quadratic, degree 2, we only turned around once. For a cubic, degree 3, we can turn around up to twice, right? For quartic, degree 4, we can turn around up to 3 times. So, right, we can have a couple of mins here and a max, right? Or if we have a negative coefficient the other way around, 2 maxes, 1 min. But you don't necessarily need to turn around 3 times. The most basic graph, y equals x to the 4th, just turns around once. Okay, so let's take a look at a polynomial, and I mentioned what window we should be operating in. So let's clear this guy out. So x to the 4th, x cubed. And just pay attention as you're walking through these that, sometimes when you're working up in the exponents, it'll keep you up there. So make sure that you scroll to the right to pull down from the exponent. Okay, let's go adjust our window. So the x values are fine, but it looks like our y values, we want to go negative 100 to positive 100. All right, let's graph this. Okay, so we have a quartic function, meaning a degree 4. Right, so it makes sense that the two endpoints, because this is even, the two endpoints are going to agree, the end behavior. And we have 3 turnaround points, right? 1 less than the degree here. Find the coordinates of the extrema. So we have 2 minima, and then we have 1 maximum. So we can go over to our calculator here and say second trace to calculate. And we have a couple different options, but definitely we see, oh, hey, minimum. Great. Let me find this minimum. Then we just have to scroll to the right spot here. So let's scroll a little bit to the left of our min and a little bit to the right of our min, hit enter. And then it's going to give us that point. And if we want the coordinates, that just means we're going to want the x value and the y value. So negative 3.17 and negative 30.98 if we're rounding. And there's going to be another one. For the max, right, let's go second trace. 4th one is a max. So left bound somewhere here, right bound somewhere here, hit enter. So our max is going to be negative 0.12 comma 48.25 if we're rounding. The second min I'm maybe going to come back to if I need, but I think that's fine. We showed how to find one of those, so I think you can go through that. As far as these go, remember these are local. Clearly we see that this function is going to keep growing to the 2 sides, so our max certainly is local, and one of these mins is lower than the other. It turns out this first min we found is actually what's called the global or universal min. It is actually the lowest point for the entire function. Okay, the domain and range. So domain is going to be all real numbers, right, as it is for every polynomial. The range, though, here's where we can say, well, I found the lowest y value that I could use in my first min. That lowest y value was negative 30.98. I could use everything above that, but nothing below it. And I did actually reach that point, so let's use a bracket for that lower bound there. Okay, and finally, let's look at this function p of x here. We're going to find a bunch of different aspects of this. So let's take a moment here and pop it into our calculator. So we've got x cubed. Again, you can use that caret, but just make sure you hit the right arrow so you're not in the exponent anymore. Plus 3x squared minus 4x. We might need to change the window. It looks like it's okay for this one. Probably the y values, we don't need to go quite so low. So maybe we'll say like minus 20, yeah, negative 25 to positive 25, something like that. The graph might look a little bit better that way. Okay, so we could copy this graph right over. That's no problem. But let's look for the intercepts here. There's a couple of ways that we could do this. We could try to factor. We see certainly that there's an x that could come out of all of these. So we could say like, oh, p of x, if I factor out an x, I get x squared plus 3x minus 4. And we could say like, well, maybe this thing factors. It turns out it does. X plus 4 and x minus 1 is how that would factor. So it makes sense if we look at our graph. We have zeros at 0, negative 4, and positive 1. So we can toss all those in. And then just sort of copy the shape of the graph that we've got. But of course, we can verify this through multiplicity, right? All of these zeros have multiplicity 1, which is why we cross over the axis as we're going. So our intercepts are going to be negative 4, 0, 0, 0, and 1, 0. Our local min and local max, of course, we can use our calculator again for those. But before we do that, let's just do our domain and range while we're here. So our domain is going to be all real numbers, right, as it is for all polynomials. The range, because we have an odd degree, the range is going to be everything, right? We're going to, as we go to the left, we go down. As we go to the right, we go up. So we're going to be able to hit every value possible. And then if we want to find our local min, local max, we can just go to second trace. Let's find our min. So go to the left of that min, go to the right of that min, hit enter. And there we go, our min. If we're looking for just the minimum value, that's different from the minimum point. So the minimum y value is just negative 1.13, but we could certainly include the point. And then if we want to calculate the max, we'll just go to the left and to the right, click enter each time, and then enter again. And our max y value, again, we could write down the point, but our max y value is 13.13.